So earlier this year, I had to fix this top of one of my sheds. We needed to waterproof this, we needed to protect it, and we wanted it to look good. So what I did is I had a number of squares and pieces of wood that I had cut from what I collected and salvaged, okay, various different sizes and shapes. And we tried to figure out, could we find a way to put these on here that would cover all of the space and protect it, right? In other words, could I tile the top of this shed with these pieces of wood, okay? You can see some of them are not perfectly square, so I actually had to trim some up, okay? Had to make them so they were more even. This one actually is a scrap piece. You can see it broke so much. But eventually, we were able to find a pattern using these pieces of wood that covered the entire space. And that's what we're looking at here. Okay, this is all made of pieces of wood that are mostly rectangular. Some are square, but they fill pretty much the entire space. Another place you will sometimes find this sort of pattern are things like a walkway. You can see there's a repeating pattern of squares of concrete that are all lined up and organized. Okay, next to it, I actually have a brick walkway that we made. You can see it's not even. There's a little more overlap on the pattern. And then, of course, you have a brick retaining wall. And if you look at the brick retaining wall, it's a repeating pattern, but so that each end overhangs, or each brick overhangs the gap in the layer below, which allows a brick wall to be strong and stable. And of course, that also allows you to make brick buildings. So the entire building is made of the same sort of alternating pieces that overlap each other to provide strength. When you create a flat surface that has a repeating pattern like this, it's called a tessellation. Some are very simple, like this. Some are a little complicated. This path works, but it doesn't have to be strong. It doesn't flex, unlike a wall, which also has to be strong. So that's a simple repeating pattern as well. But all of this is called a tessellation. So the first thing we're going to do next is I'm going to take you to a website where we can explore tessellations, and you can learn a little bit more about what they are. So let's go check it out. This website gives you a bunch of tools to explore tessellations. The first one we looked at was the simple path. This is like the concrete pavers that make up my walkway. Right. Of course, which can change the colors of things to make it more aesthetic. But you can see that you could easily create a simple pattern that fills the entire space. When we look at the brick wall, we have what are called courses, a course of bricks. There's one horizontal layer. Bricks, of course, are rectangles. You get more of an overlap. The idea, oops, you won't actually let me overlap. Interesting. But the idea is you would have a brick here, so the ends go on 2 bricks to the sides, which helps it to be stronger. But it's still a pattern that fills the space. You can make tessellations with any of these polygon shapes at the top. Some of them like to be square, fill the space easily. Some of them, like the triangle, will fill the space, but you have to do some work to get it to fill the space. So here we go. Actually turn. So now if we wanted, we could copy, copy, copy. If we say copy again, and then move this one here, of course, copy, copy. And so you can already see how it would be easy to fill the space just with these triangles. Other polygons, you can still make a tessellation, but it doesn't fill the space exactly. So for something like this, for something like so you can see it gets a little more complicated, and you have to do some more thinking and planning ahead. And especially some of these bigger shapes, if you almost want to fill the space, but you have to have some odd shapes inside of it. Okay? And so at the end of class, I'm going to let you explore this tessellation maker and see what interesting patterns you can make. But this is the one I especially want to talk about. The hexagon is special, right? We've talked about hexagons in the past when we talked about snowflakes. What makes hexagons interesting is that they will fill the space completely just using hexagons. Okay? So you don't need any other shape besides the hexagon in order to fill the space. It fills the space completely, and it's actually a very strong shape. One of the reasons that you find lots of hexagons in nature, the snowflake being just an example, is that it is a very strong yet pretty simple shape to make. So lots of different either organisms, animals, or processes like water freezing into a snowflake can take the shape, take the form of the hexagon. Let's take a look.
You know, hexagons are the Bestagons. Why? Because bees. Bees are the best and build only the Bestagon, the hexagon. Now, I know what you're thinking. Bees build hexagons because they're hexapods with hexagon eyes. How could they do otherwise? Excellent point. But the Humble Bumble has an engineering problem to solve. She makes two things, honey and wax, the former to eat and the latter to contain the former. To make but a little honey, she must visit a lot of flowers, and to make 1 unit of wax, she needs 8 units of honey. Wax is costly for bees in flower terms, and honey is drippy in food terms. So to make a hive that contains the maximum honey while using the minimum wax is royally vital. Thus, a honeycomb conjecture. Which shape works best? To answer, we need to talk tiles. Tiling is covering a surface with a pattern of polygons. There's lots of options because there's lots of polygons. Even the regulars go on and on-agon. Now for bees picking patterns, the more complicated ones obviously use more lines than necessary. That's what complicated means, and thus a honeycomb of that tile would use more wax per honey. So sticking to the simple regulars, there are just 3 that tile tightly: triangle, square, and hexagon. Pentagons are broken hexagons, leaving gaps, same with septagons. Octagons are alright, but they're no hexagon, which leaves the tiling trio which tile differently. A square is a square of squares, which is a square of squares, and so on. Squares tile tidily by basically cheating, covering an infinite plane with an infinite number of parallel lines. Like, wow, that's what a plane is. Boring. Triangles pull the same trick, dividing themselves down into infinite nothing. But not the hexagon, the only regular polygon to tile a plane without resorting to debasing self-division. Unlike some squares I could mention, at least triangle is trying to be more geometrically interesting than square, teaming up a bit to 1, 2, 3, 4, 5, 6. Wait, hexagon! The other shapes can't help it, they just want to be the bestagon. Even some of the irregulars like rhombus tile by hexagoning. Same with your tracheus tiles and deltoid trihexanogals and your crystal rhombles and florid pentanogals. Look, they're all just hexagons. Even chirotiles, poor pentagons, tile up as best they can to form a lumpy hexagon. The rest just can't compete with the best. The hexagon nobly indivisible is the bestagon. Where were we? Oh right, honeycomb conjecture. Max honey, min wax, 3 options. Okay, yes, there's the circle, a shape defined by the least perimeter for the most area, but that only works when you need just one. Pack circles and this is the best they can do. Look at all that wasted space. And even if you pack the gaps, you still use more wax. And again, the way these circles arrange themselves, it's almost like 1, 2, 3, 4, 5, 6 hidden hexagon. Bees use the hexagon because no shape is better to create the maximum area for the minimum wall, and this min-max stat of hexagon is one of the many reasons they show up everywhere, including in the aforementioned bee's eyes. Each hexagon is a long tube that leads to the light-catching cells at the bottom. More light equals better vision, and hexagons let the most light in using the least amount of wall. So why aren't your eyes hexagons? Au contraire, mon ami, they are le hexagon. Not on the outside, but on the inside. Your light-catching cells are at the back of your eye, in a hexagonal grid for the same reason as bees. Max light, min wall. Your window to the world is but through the hexagon. Does that not make it the bestagon? Okay.
When I was growing up, one of my favorite artists was a man named MC Escher. MC Escher made very complicated, technically proficient art that was mathematical in its base, but offered either repeating patterns or paradoxes, right? Very interesting things to look at. So very clean technical drawing, but when you start to look closer, you wonder, wait, are all four sides of that tower feature people walking upstairs? How can you have people walking upstairs on all sides? Right? That's not how stairs work. So this is a paradox, right? Which he did a lot of artwork like that was weird and surreal and warped. But I often tended to like the things that were built off of tessellation, right? And tessellation is what we've been talking about. So images like this feature, it's a picture of a picture, right? And the picture he's drawing on the paper is a tessellation, right? You can see there's a hexagon grid that he put down so he could work off of. And then there are rules that say if I take away this shape from this part, I need to add it to that part. And by doing that, you can create a repeating pattern that will fill the space. And so that's what this was. This is one of his tessellations that he was known for. And then he drew it on the paper and expanded that idea out where, say, right here, these lizards are coming up off of the page. They circle around and then go back into the page up top. So simple rules to make the tessellation. Subtract it from the part from here, add it there, and you get a repeating pattern. And he expanded that out into real space, into the 3D world, by making the lizards come out and be real and then return to the picture. He also did things that were a little more abstract. Right, you can see the floor is tessellated at the top, and then the side of the building starts with that same tessellation, but it devolves. At each point, the tessellations match, but they get slowly more and more complicated and come down to be this figure, which starts out photorealistic at the top, ends up being the tessellation here at the bottom. So this is a complicated picture that isn't based in like a real world drawing, but the idea is the simple transition from something realistic to something repeating pattern. And it's all built off of coming up with this tessellation first and then extrapolating it out to the real world. Even further along that path, he would make things like this. This looks just like an image of a pond, right? You might see this in the real world, but it's got that same idea where it feels like you have realistic leaves down here and you have abstracted leaves up top. Even though it's all built in nature, a lot of his work was exploring how this sense of repeating patterns came about. So these more like abstract ones that aren't as realistic, like this, are about exploring how those patterns come about in the real world. One of the places that Escher learned about how to do this, about how to take these simple rules and use them to make repeating patterns, was by studying Islamic art. Right? Art in the Islamic world is built off of simple rules to create repeating patterns that are complex in nature. So simple rules make complex patterns. The art that comes out of that is stunning. It's beautiful. It's complicated, and it seems inhuman. Like, how could humans make patterns at this scale? But it all comes from simple rules. And studying those simple rules can lead you to understand how complex patterns emerge, right? Tessellation is simple. You fill a space, you tile a floor, it can be super simple. Hexagons are the Bestagons because they tile the space but are also strong and efficient. But they're not the only way to do it. And if you allow yourself to worry about the aesthetics, the beauty, as much as the strength and the coverage, you can get things like I'm about to show you with the Islamic art. But it's all built off of the simple rules of how do you fill the space using repeating patterns. Let's take a look.
In Islamic culture, geometry is everywhere. You can find it in mosques, madrasas, palaces, and private homes. This tradition began in the 8th century CE, during the early history of Islam, when craftsmen took pre-existing motifs from Roman and Persian cultures and developed them into new forms of visual expression. This period of history was a golden age of Islamic culture, during which many achievements of previous civilizations were preserved and further developed, resulting in fundamental advancements in scientific study and mathematics. Accompanying this was an increasingly sophisticated use of abstraction and complex geometry in Islamic art, from intricate floral motifs adorning carpets and textiles to patterns of tilework that seemed to repeat infinitely, inspiring wonder and contemplation of eternal order. Despite the remarkable complexity of these designs, they can be created with just a compass to draw circles and a ruler to make lines within them. And from these simple tools emerges a kaleidoscopic multiplicity of patterns. So how does that work? Well, everything starts with a circle. The first major decision is, how will you divide it up? Most patterns split the circle into 4, 5, or 6 equal sections, and each division gives rise to distinctive patterns. There's an easy way to determine whether any pattern is based on 4-fold, 5-fold, or 6-fold symmetry. Most contain stars surrounded by petal shapes. Counting the number of rays on a starburst, or the number of petals around it, tells us what category the pattern falls into. A star with 6 rays, or surrounded by 6 petals, belongs in the 6-fold category. One with 8 petals is part of the 4-fold category, and so on. There's another secret ingredient in these designs, an underlying grid. Invisible but essential to every pattern, the grid helps determine the scale of the composition before work begins, keeps the pattern accurate, and facilitates the invention of incredible new patterns. Let's look at an example of how these elements come together. We'll start with a circle within a square and divide it into 8 equal parts. We can then draw a pair of crisscrossing lines and overlay them with another 2. These lines are called construction lines, and by choosing a set of their segments, we'll form the basis of our repeating pattern. Many different designs are possible from the same construction lines, just by picking different segments. And the full pattern finally emerges when we create a grid with many repetitions of this one tile, in a process called tessellation. By choosing a different set of construction lines, we might have created this pattern, or this one. The possibilities are virtually endless. We can follow the same steps to create 6-fold patterns. By drawing construction lines over a circle divided into 6 parts and then tessellating it, we can make something like this. Here's another 6-fold pattern that has appeared across the centuries and all over the Islamic world, including Marrakesh, Agra, Konya, and the Alhambra. 4-fold patterns fit in a square grid, and 6-fold patterns in a hexagonal grid. 5-fold patterns, however, are more challenging to tessellate because pentagons don't neatly fill a surface. So instead of just creating a pattern in a pentagon, other shapes have to be added to make something that is repeatable, resulting in patterns that may seem confoundingly complex but are still relatively simple to create. Also, tessellation is not constrained to simple geometric shapes, as M.C. Escher's work demonstrates. And while the Islamic geometric design tradition doesn't tend to employ elements like fish and faces, it does sometimes make use of multiple shapes to craft complex patterns. This more than 1,000-year-old tradition has wielded basic geometry to produce works that are intricate, decorative, and pleasing to the eye. And these craftsmen prove just how much is possible with some artistic intuition, creativity, dedication, and a great compass and ruler.